Hi guys, can I get a sound check?
Hello.
Hi,
Testing.
thanks. Thanks, Jonathan.
Hello?
Yeah, hi Salvador. Thanks. Let's see, what do we got here? Let's see. Okay, guys, let's get started. So I was gonna kind of have a short lecture today, let you guys go. Probably like after about half an hour, 45 minutes to cover a few things. I wanted to just cover first the syllabus, to talk about sort of the logistics of the class. Then I'll talk a little bit about my background, why, what qualifies me to teach the class, and kind of how I view what I can bring to teaching you guys about chip design. Then I'll talk a little bit about the sort of semiconductor business and stuff. And I think that's going to be pretty much it for today. So just on the logistics, my name is Barmak Mansourian, or the office hours are Fridays from 9 to 11 a.m. And the office hours has a separate Zoom invite. And separately from that, I've got my email here, my phone number if you guys want to text me or whatever. Reasonably available, I think. Hopefully I can get back to you guys reasonably well. It sometimes gets a little patchy, if I've got something going on. I'm not a regular Cal Poly prof. I'm a lecturer, so most of what I do is sort of It's Cal Poly related. All right, so this class is intro to, what is this class? Intro to VLSI design. And so VLSI design now is almost entirely CMOS technology. And so we're going to be talking about, and I'll talk about the different degrees of abstraction in a microelectronic system. And by the degrees of abstraction, I mean that, it can range anywhere from, if you think of say a cell phone, you're looking at abstraction, the highest level of, the application programs, et cetera, down to the operating system, the OS, down to the embedded programming, down to the, like Verilog. I don't know if you guys have played with that code, that you can just define a circuit, to circuit blocks like a memory, to actual circuit. These are going sort of in degrees of abstraction down to, circuit design, to transistor design, to process design. The process, when you're designing a single transistor all the way to designing the whole cell phone. So we're in a certain part of that area of abstraction. Basically, we're mostly talking about circuit design, a little bit about sort of sub-circuits like clock generation and distribution. We're going to be talking about, memory, maybe memory systems, how to analyze noise, say. And then we're going to be talking a little bit about a level of abstraction below that, which is the process technology, how these devices are built, and so on. How to optimize speed, area of power from a circuit standpoint. So it's primarily a circuit class. Now let's see. I don't know how I can take a vote from you guys. I'm assuming at least a significant number of you are in computer engineering. I guess there's no way to do a hands up or anything, but maybe there is, and I don't know it. But anyway, thanks, Arvind, for raising your hand. So anyway, we're going to be, I think the computer engineers in some ways have some advantages in the class because they might have heard about some of these sort of more system aspects. The electrical engineers are maybe more familiar with the transistor aspect. So everybody's going to be coming in from a different angle slightly. Okay, so in terms of the different areas, again, I talked about this a little bit. We're going to get into it. One thing that we are seriously lacking because of the whole remote work is at the moment we don't have access to the computer-aided design tools, which are really, really a big part of chip design. So, Dr. Olson is, she's trying very hard to, we've been trying last semester, and we're still trying to somehow get access to the CAD tools. I hope we'll get access to the CAD tools during this class. I'm not sure, but in lieu of the CAD tools are really, really a big part of things. But in lieu of the CAD tools, and while we get that access, we're going to be using just simulation, SPICE simulation, which is, a pretty big part of the whole CAD environment. But we're going to have to use this, something simpler. And my suggestion is LT SPICE, and it's a free SPICE simulation tool from Analog Devices, and I like it because it's available both on the PC and the Mac. I have it, and I have a little YouTube tutorial session with some example files and stuff for you guys to get started. So I think we'll be using that. You're welcome to use, if you guys want to use PSpice or CAD, it's up to you guys if you want to use those. But just beware that I don't have those, and so when it comes time to the projects, etc., I can't really help you if you're running into some PSpice related thing. But if you have LT-Spice, I can probably help debug the circuits a lot more. So, I would sort of suggest that, unless you're, anyway. So let's see, what are some of the other things? So the book is West and Harris. I think a lot of you guys don't like to buy books anymore. It's a good book. It's a little bit dated. I think it's 2010, but I don't think there's any, like, I haven't run across a better book. There's this other book, Rebay from Berkeley, and it's a pretty good book. I think they're both pretty good books. I don't know, I don't know what to tell you guys. It's sort of a guideline. I don't know if you need the book. It's, I'd suggest you buy it, but I think we could definitely use a refresh in terms of textbooks in this space. So let's see what else. In terms of the logistics, let's see. See the grading. Here's the grading. So we're not going to have a final. We're going to have 2 midterms, 2 equally weighted midterms. And, the second midterm, I'm not sure about when the 2 midterms will happen. It says week 14. I'm not sure. It might actually, the second midterm might actually, sometimes more often than not, it's ended up on the day of the final. But it's only going to cover, the second midterm is only going to cover the stuff after the first midterm. So once, you don't have to go all the way back to the beginning of the class for the second midterm. And then the design projects are 30%. And again, it's going to be a little bit of a struggle with the design projects because we only have access to Spice. And so we'll just have to kind of work our way through it. The rest of this stuff, I think you guys all know this, stuff. So, I think one of the things I wanted to tell you guys up front, because I know this class is a elective for most of you guys. I mean, I'm not trying to encourage you guys to drop the class. I'd love for all of you guys to be part of the class. That's why I'm teaching, is to work with you guys, and really looking forward to it. But I just wanted to kind of give you guys a heads up about my teaching style, what I bring to the class, the view that I have, and what that means for the tests. So one thing I've noticed in Cal Poly is that I think a lot of the students are used to the sort of the tests being or at least that's the feeling I get, tests being 1-to-1 correlated to homeworks, meaning that, if you're doing the homework, the test is going to be sort of almost maybe the same, similar to the homeworks, etc. And, I might do that, but really I'm from the industry. And so the way I view you guys as students is you're kind of in between a place where, when you were freshmen, et cetera, beginning of your school career, where you were being, everybody's focused on your learning, focused on you. And it's still obviously the case in this class, but soon you're going to be graduating and you're going to be in the industry, you're going to be working or in grad school. They're both similar in the sense that now you'll be looked at to be producing. You'll be looked at um, to create stuff, to do stuff. And I don't want to make the work environment seem like a cold, harsh place. I look at people I work with usually as a family. I've been very lucky, but you're in a situation where you're going to be looked at to be working with vague instructions. Nobody knows what the problem is. You'll have to define the problem, understand the problem. You'll have to solve the problem, report on the problem clearly. And so it's, nobody's going to be giving you guys a step-by-step set of instructions on how to solve a problem. And as you advance in your career, it's only going to get, things are going to get less and less well defined. The problems are going to get more and more critical and more expensive to get wrong. And you're going to be ending up reporting to a higher and higher level of management who have a bigger and bigger level of attention deficit disorder. Um, so so I don't believe in the tests are just going to be a route, and the tests are going to be at what I believe are a good indication of whether you've understood the material. And so just a warning. So if you're like looking for a one-to-one correlation from homeworks to tests, etc., I'm you might be again, I'm my tests I feel are not like, I don't try to make them hard, not a harsh grader, but I just try to, there's no guarantee then that like it'll be a one-to-one correspondence between the homeworks and the tests. Let's see what else. I think I already mentioned about the office hours, 9 to 11 a.m. on Fridays. It has a separate Zoom invite. And then I have my phone and text on there again. I think I might have mentioned those. Any questions, guys? I think that was all the stuff I was going to talk about, the programmatical stuff. Anything?
No, sounds good.
No? Okay, sounds good, guys. So then what I'm going to do is talk a little bit about my own background, because I'm not a Cal Poly prof, and tell you guys like why I think I think it'll give you guys an idea of like sort of how I view the class and how I view what we're trying to learn here. So my name is Baramek Mansourian. I got my undergrad and PhD from UC San Diego in the mid 90s. And then after that, I came up to LA to work at JPL on a technology that was just coming up back then, called CMOS image sensor technology. And this is back then it was just a research project in JPL. Now basically every camera that you use, your cell phones, etc., has this chip, this technology behind the lens. Basically, it's what takes a shot of the image, it translates the photons from the lens to a digital format that the rest of the system can work on, etc. And I've been working in that field for the last 25 years. From a day-to-day operation, there's a bunch of optoelectronics, system level stuff, but it's essentially chip design, analog and digital chip design. In my case, it's mostly analog, but there's certainly a significant part of the digital design. And, worked on in that period, 25 years, God, I don't know how many chips I worked on, to either design, to manage, to sell, lots and lots, 100 plus. So I feel like I really have a feel um, for the business. At least that, everybody sort of has a different angle of looking at technology or an environment, but certainly I'm very, very industry oriented, let's say. And my experience is, I'll talk a little bit about it, but started off doing designs, then moved into doing management, then end up doing business development, then sort of building a business, and et cetera. So um, after JPL, I was part of two other startups. One of them in Pasadena that was sold to Micron Semiconductor. I was employee number 7 there. It was a great experience. The second one was in San Diego. That again, I was an employee. Nothing. It just went sort of belly up after spending a bunch of money. Then in 2001, I started a company with a couple of friends up here in Pasadena. And in 2018, we had a successful exit. But successful exit is euphemism for we sold it profitably. And and I'm very proud to say that we had 45 employees, and as a result of the sale, nine of the uh, 9 out of those 45 people became millionaires. And a result of it, I was lucky enough that made enough that I don't have to work for a living, at least for the time being. And so I'm just sort of acting as a consultant to the company that bought us on a part-time basis, basically getting paid to read technical papers, which is a good place for a man of my advanced years. And so the reason I mentioned that isn't for self-aggrandizement. It's sort of number one of I have like sort of 4 things that I want to bring to this class, and one of them is to really encourage you guys to think about entrepreneurship or being part of a entrepreneurial company, part of a company that you can have ownership in. That usually comes in the form of stock options. So if you're going to write 2 things during this lectures, please write down stock and options, because I really want you guys to understand those work. That could be the key to early retirement. Could be lots of wonderful things if you're part of the right company. Basically, what they do is a C corporation, which is the usual way most semiconductor technology companies are organized, has a bunch of owners, and those are the shareholders. So a stock option is a typical way for people, whether you're a CEO, whether you're the founder or at the receptionist, it's a way for you as an employee to have ownership in the company, stock options. Okay, so I'd really, really want you guys to, and I'm going to be trying to figure out different ways to have you guys think about that. Whether it's pretty typical, thankfully, in semiconductor business, a lot of the areas of high tech business. It's really useful in growing companies because you get basically a chance to enjoy part of that work, not just make your salary, but perhaps make a significant amount on top of that. So let's see. So what's my connection to Cal Poly? Well, a big number of the group of 45 people that we had were Cal Poly students that we'd hired straight out of Cal Poly undergrad that joined our company, and basically Whoops. Running out of battery. Oops. Sorry, guys. Just you guys still with me?
Yeah.
Yes.
Yep.
I might have lost my.
Good.
These are kids we hired out of kids. They're like men now, but men and women. But we hired them out of Cal Poly, and they really helped. Not just helped; they really built the company. And so, this is how I feel like it's my way of bringing some of that learning, some of that experience back to Cal Poly, and hopefully, again, infect you guys with some of my mental models of how the world works and what you should do with your career, at least what the possibilities are to do with your career, whether, it's to get into the semiconductor business, which I think is, a lot of fun, very interesting, lots of stuff going on, certainly a passion of mine, but definitely be thinking about how you can be involved with the business of whatever company you work for. Whether it's Northrop, I don't know the name of the DoD companies, I'm not very involved, but whoever it is, it's important for you guys to think of yourselves as part of the running of that company, even at the lowest technical level, all the way up to when you'll be VP of engineering or CEO of the company. Really helps to have that view. And on top of that, I'd really like you guys to be thinking about how you can get actual ownership in the companies. It's always partial ownership, whether it's 100 shares or 50% of the company, whatever. And then, I think it's fantastic to think about building your own companies. And it's one of the great, I think it's one of the great perks of being in the tech field, whether you're EE, CE, CS, whatever. You really have a legitimate opportunity if you want to build your own company. I don't know if a lot of other fields. I think you can build a business in any field, but it's definitely more common in technology. Anyway, so that's my background. Any questions about that? Okay. If not, let me just talk about what is VLSI design, what's microelectronics, sort of the really, really high level view, the way I see it. So I always have to look this up every semester. So I ended up looking it up again this morning. But the transistor was invented in 1947. Okay, so that's 73 years ago, I guess, 74 years ago, something like that. And then when it first got invented, it was seen as kind of a one-to-one replacement for something called a vacuum tube, which, I've never worked on, but some of you guys might have heard about, maybe not, but it was, a vacuum tube was a way to create an electronic switch. Semiconductor is a solid state semiconductor-based switch, essentially, a controlled switch. And it took a while, and it took until 1960. So from 1947 to 1960 is when people started thinking about putting more than one transistor on the same semiconductor substrate. And that started this process where every 2 years, roughly, every 18 months, the number of transistors in a semiconductor chip would double. And this is something you guys, again, might have heard of, called Moore's Law. So thanks, Danush. Exactly. So it's Moore's Law, which stated that the number of transistors per semiconductor chip would double every 18 months. Okay. So unfortunately, because we're in the middle of a pandemic, I think you all now have a good idea of how this kind of exponential growth can look like. And so, you started in 1960 with 2 transistors, you doubled the number every 18 months. By 2019, which is the last year I could get data for, the record for the largest number of transistors per chip was in a NAND flash chip, and it had 2 trillion transistors in that chip. And I don't know the size of the chip, but I'm going to guess it's about probably 10 by 10 millimeters size. So 2 trillion transistors. And the record for the largest number of transistors in a processor chip was an AMD chip that had 40 billion with a B transistors. So it's this exponential growth. And so it's kind of in its own way eating the world. Basically, everything around you is somehow being controlled by the chip, being observed by the chip, and it's only going to be more so as time goes on. So just as an example, just something that's probably pretty obvious for you guys, but probably within arm's reach of you guys, there's a trillion or 2 transistors. And if you use the example of your cell phone, the iPhone 12 has the chip that's designed by Apple. It's called the A14 Bionic chip. It has about 12 billion transistors. Okay, so your laptop, and if you use a MacBook Air as an example, that has the M1 processor has 16 billion transistors. And each one of them probably has somewhere between, 16 to 64 gigabit of memory. And those are billions of transistors, giga, that's what sort of stands for billion. And then your solid state memory is in the hundreds of gigabit, which again is hundreds of billions of transistors. So, you probably have about 1 trillion transistors just within arm's reach, sitting in front of you on your desk or something like that. And it's really not just, those are kind of obvious places for transistors to be, but you can think of automotive cars now, not just Tesla, but any car. A significant part of the bill of materials, the cost that goes into a car, is semiconductor content. I don't know if you guys are looking at business news, but there has been a shortage of chips for the automotive space. And sort of famously, I think it was in January 13th of this year, Honda even had to shut down a production line in England because they ran out of chips. And I've worked in the automotive space, and I can tell you when those production lines shut down, it's very, very expensive and very, very bad news for the company. So all this so sort of brings up to where we are today. It's basically, it's a pretty big business, the semiconductor business. So if you add up the market valuation, means that how much the value of these companies are in the stock market. For the semiconductor companies that are listed in the stock market, you're talking about $4 trillion. And so these are all the companies like, Intel, NVIDIA, companies that are only making semiconductors. So that's their valuation. But it doesn't include, companies like Apple, like Google, like Facebook, Amazon, that are actually starting to design their own chips. For example, those chips, the processor chips I mentioned in the iPhone and the MacBook Air, are both designed by Apple. And Google designed its own server chips. Facebook, um, Danush, are you asking what's your question about RISC-V? This is a kind of a really interesting topic, actually.
Yeah, I was just curious because then it seems like the current trend is the industry is migrating more towards RISC-V,
Yeah,
like one chip and other ones.
yeah. Thanks for bringing. I'll put that in context in a minute. Thanks for bringing that up. Um, so and so let's see, where was I going with that? Yeah. So anyway, so it's a growing business. It's already a very, very big business. So that brings us to this year, let's say the last few years. But so what's happened though, I would say if I was teaching this class 10 years ago, although I love the semiconductor business, I'm not sure I would have recommended you guys to go in the semiconductor business as young new engineers, because the way what was happening is, again, sort of counterintuitive, but because of Moore's law, um, companies just stopped being interested in designing their own chips, because what Moore's law was doing is every 2 years, every 18 months, the amount of processing power that you could just buy off the shelf from Intel, from AMD, NVIDIA would double. So it wasn't really a smart idea to spend a bunch of money and effort designing your own chip if all you would have to do is to wait for those guys to introduce the next chip, and you were just always guaranteed that you would have this increase in performance. And again, that was because of Moore's law. But like any other exponentially growing type of thing, just like we're seeing with the, using a lot of COVID examples, nothing really stays exponential forever. After a while, things tend to taper off as the total population grows. And that's happening, that's been happening with Moore's law the last 4, 5, I don't know, 6, 7 years, to the point where people are talking now about whether Moore's law is dead, in the sense that certainly the number of transistors per chip are no longer doubling every 18 months. Again, going back the last 10 years or so, it's really turned into every 3 to 5 years where the number is doubling. And there's a couple of reasons for that. And we'll touch on both of these in the class. The first one is power consumption. So each one of these transistors you're packing into a chip, when it's operating or when it's not operating, it's burning some amount of electrical power, which directly transfers to heat. And it turns out that removing heat, it's a thermal problem. There's no easy way around it. It gets very expensive and even impossible at some points to remove the heat from a chip once you get just too much power density, heat density in that chip. So that's just been setting a limit. People have been working on, and we've had huge improvements in reducing power consumption, but that just hasn't been enough that we can continue on that exponential growth curve. So that's one reason, is power consumption. The second reason is that the other thing that's been exponentially growing is the cost of building new semiconductor plants. So the way that we've been putting in increasing the number of transistors per semiconductor by 18 months, every 18 months, is by shrinking the size of those transistors with every generation. So for example, the first iPhone that came out, I think it was in 2006, was using a 90 nanometer CMOS process. That's 90 times 10 to the minus 9 meters. and I don't know what context to put that in. You know, a human cell is 10 times 10 to the minus 16 meters. So a human cell is like, I don't know, 1,000 times, is that right? 1,000 times bigger than that, 90 nanometers about. I think a bacteria is like maybe 1 micrometers. And I think a virus is like, you know, take this with a grain of salt. I'm not a biologist. I think a virus is about 300 nanometers. So this is a transistor that's like a third the length of a virus, say, so 90 nanometers. That was in 2006. These latest chips that I just mentioned, an iPhone 12, et cetera, are built in a 5 nanometer process. So it's, you know, in a process that's sort of in a linear dimension. What is that? Is that 90 to 5? That's 18 times smaller. That's in a linear dimension. And when you think about area, it's sort of the square of that. In some ways, it doesn't quite work that way. But we went from 90 nanometers to 5 nanometers. So another way to look at 5 nanometers is that, you know, blue is the shortest, just about the shortest wavelength the human eye sees, and that's 400 nanometers. So, you know, there's no way you can, you know, use a microscope, any kind of microscope. You can't use a light, you can't use light to see these transistors. You have to use scanning electron microscopes, et cetera, just to even see the transistors that you're trying to build. And, you know, if you look at, we'll look at this in a little bit, but even if you look at the size of an atom of silicon, it's not a whole lot of atoms that, you know, go into 5 nanometers. And so, you know, as these processes are going from 90 nanometer to 65 nanometer to 45 to now 5 nanometers, they're working on 3 nanometers, et cetera. The cost of these manufacturing plants is, you know, we're talking about many, many, many $billions to build a single manufacturing plant. And those companies that build those manufacturing plants somehow need to recover that investment. So all that means that they try to squeeze more out of that investment to pay back that initial capital investment. So they want to use that thing for, you know, milk it for a longer time and not keep building new manufacturing plants. Anyway, that combination, those are the two major issues for Moore's law slowing down significantly. So what does that mean to the semiconductor business? Well, it's been actually really good for semiconductor designers and design houses, et cetera, because, you know, now it no longer pays off just to sit and wait for Intel, NVIDIA to use Moore's law to come up with a higher performance chip in a couple of years. Because it's just that day might never come, and it'll just takes too long to improve your performance. So more and more companies now are designing their own chips because, you know, they can't really use improvements in process technology. What they can do is use their knowledge of how their own system works. You know, Apple knows how their operating system works. They know the rest of the components in their system. They know their user base. They know how their users are going to use their computers or cell phones, et cetera. And they can use all that knowledge to make a chip that is very customized to what they're doing. And so, so this is basically this is what's sort of an exciting thing for you guys. I think if you're interested in getting in the semiconductor business, I think it's a good time, because for the next 10, 15 years, I think that that kind of stuff is going to be proliferating. Now, coming to risk 5 that Danush mentioned. So because, so like, let's say going back 10 years ago, people would buy, Intel chips. And this was, Intel architectures. These are stuff that's architectures that are owned by, say, Intel, by AMD. There's been another company called ARM, which has owned a big part of the excuse me, the processor IP space. So if you, say over the last 10 years, if you've bought a mobile chip or automotive chip or something like that, chances are it would have one or several ARM processors. But again, this ARM processor, it's a RISC architecture, reduced instruction set architecture. You guys know more about it than I do, but but you still have to license from ARM. You have to pay licensing fees, or et cetera. You can modify it yourself. So a few years back, there was there's a group at Berkeley who came up with this open source RISC architecture called RISC-V. And it was really made as sort of for academic use because it was open source. From a research standpoint, et cetera, you could basically change it to suit your needs. It wasn't a closed system like an ARM chip, ARM processor architecture, or Intel architecture where you couldn't play with it. So it was an open source architecture. And what happened over time is actually companies started using this RISC-V because it was open source to design their chips. And coincidentally, it became very popular, for example, in China, because a lot of Chinese companies didn't want to pay royalty fees to ARM. They're trying to build their own sort of homegrown systems, et cetera. So it really caught on, this RISC-V architecture really caught on in China. It's really caught on with people who want to design their own chips. Like I mentioned, a lot of people are trying to design their own custom chips now. And a big part of the expense of building your own chip is all the licensing fees that you have to pay to various vendors to buy the different components from. So for example, let's say you have a chip in your system, it's doing something. So it's, I don't know, say controlling a chip, controlling a switch. So it's doing something really simple. But you need a microprocessor in there. So traditionally you would have had to go license a microprocessor architecture from ARM, pay them, whatever, depends on the processor you wanted, probably multi-million dollars. Just that's a licensing fee so it could use it in your chip. And then, typical chips, you need to have, say, a memory interface. Memories have this architecture, this interface architecture is called DDR. I don't know if you're familiar with it or not, but take my word for it. So you'd have to license that. You don't want to build all this stuff from scratch, or it's going to take you forever to design your chip. And so all these, let's say you need it for whatever reason to interface to a PC. Now you need a PCIe interface to interface with your PC. Or if you had a Wi-Fi connection, you would need a Wi-Fi interface. So you don't want to build all this stuff from scratch. You have to go license it, and it just blows up the cost of your chip to the point where it doesn't make sense to design your own chip. So anyway, this RISC-V has been really caught on for semiconductor business with this whole thing about building chips, et cetera. And there's lots of startups working on it, et cetera. It's interesting that I'm assuming you guys are also pretty aware, or maybe you're not. it's probably better not being listening to the news. But a big part of the friction between U.S. and China is over the semiconductor business, because China's identified semiconductors as, and being sort of independent from a semiconductor standpoint, one of its key national plans, I say, with lots of money being poured into it. And the U.S. is, I think, quite concerned about what that would mean for competitiveness, et cetera, and its own supply. But it's been putting all these trade restrictions on. I'm sorry, guys. So it's been putting all these trade restrictions with selling semiconductors to China, et cetera. So interestingly, the committee that I think it's the committee that's overseeing RISC-V, just recently, I think end of last year, moved to Switzerland, moved their headquarters to Geneva, so they wouldn't be limited, because they're a U.S. company, to be able to work with China. So lots of interesting stuff's happening around the semiconductor space, and both from sort of global strategy, just business, interesting new things happening. So I think it's a really cool time to be getting into the semiconductor business. But it's just something that again, I don't think I'd be able to tell you that 10 years ago was kind of getting to be a kind of a boring thing. But now a lot of fun stuff, a lot of interesting stuff's happening, lots of opportunities, hopefully, for entrepreneurship, putting your mark on the world, et cetera. So that brings us to 2020, 2021, where we're sitting at. Again, Moore's law is slowing down, and more companies now are building their own chips, whether, again, lots of companies, et cetera. The other two trends that are sort of our corporate masters, it's getting clear that this is where things are going. So, like it or not, and I'm just joking about corporate masters, because we love those corporations. They give us our paychecks. But two major things are going to be, I think, driving semiconductors even harder. And this isn't stuff I've cooked up. It's the whole semiconductor industry believes this to some extent, is that there's definitely a trend for more AI getting sort of in all areas. So artificial intelligence chips, neural networks, et cetera. A lot of those chips are being custom designed to get performance, power consumption, et cetera. And they also do tend to be pretty specialized chips, AI chips. So there's a lot of activity in designing AI chips. So that's a whole new space. And then, I'm not an expert in artificial intelligence or neural networks or anything, but a huge part of AI is having data to feed your AI system, to train it, et cetera, to increase its capabilities. And to the point where we're running out of data. I mean, the entire data, I keep hearing about the amount of data in the internet being huge and growing by huge amounts every day, is still not enough to the level that AI algorithms, are to satiate them, to, for them to get better and better to the point where, I guess it depends on what point you're talking about, to more sophistication. They're just constantly looking for more data. And what that's causing is this whole new market called IoT, which stands for Internet of Things, to generate that data. And what that is smarts internet connectivity in things, in your light bulb, in your thermostat, in your door lock, in your glasses, I don't know, in your comb. Um, is this There's just gonna be all this semiconductor content everywhere, collecting data and sort of feeding the machine to figure out how to automate and sort of make smarter, better, hopefully, our lives. So all that means just is a lot more growth in semiconductors. Just that's becoming more and more obvious every year, that that's kind of a direction that semiconductor business is going to, on top of all the other content, semiconductor content that's been going on. So let's see. I think that was my thoughts on the business. I think, what else did I want to say here in this class? No, I think you guys are all, pretty close. You guys are all, I think, probably seniors, or I don't know if there are any grad students in the class, but getting pretty close to graduation. So I think you're getting a better view of the overall technology. But I want you guys to also remember that, if we were, I don't know if you guys are interested in martial arts or not, but at least some martial arts have this belt system. When you start, you get a white belt, and you have all these color belts, and by the time you are considered a fully formed student, you get a black belt. So it doesn't mean like everything and everything, but just means that you're kind of ready to learn on your own or contribute on your own, etc. So if you think about that as the engineering training programs, when you're a freshman in undergrad, you get your white belt, and you don't get your black belt if you're going to academia. You probably don't get your black belt until you've gotten your PhD and a couple of years experience, or after a BS or master's, you worked in industry for 7-10 years, something like that. Until then, you're not in a position where you can be an independent contributor. So you guys are closer to the beginning of that process, maybe getting on the halfway point, hopefully. But I think you guys need to start thinking about transitioning from your academic, even if you want to get into grad school, it's just PhD programs, et cetera, are very different than undergrad programs. So sort of start thinking in the mode of how you look at problems, getting used to ambiguously defined problems, getting used to communicating your ideas well, and understanding what your role is in an organization and how you can add value to the organization as part of your role, because that's how you advance in any place you go to. Is the more value you bring into the system, the fastest further you will advance. It's just the way companies work, thankfully. Now, you could be adding a lot of value and still not advancing because you don't know how to communicate. You don't know how to sell your ideas, etc. So you need both of those. But you could be like a good talker and not have the technical meat, and you still really, I don't think you're going to do as well as you would if you have both. So I'd like to work on that with you guys, and I'm going to be looking for you guys to be, where we're talking about turning in your reports, otherwise communicating, etc., start, getting into a more polished communication style. You're not going to be writing War and Peace. That's not what we're doing. But in fact, you want to keep things short, succinct, clear. Like I mentioned, I don't know if I mentioned this or not, but the further up you go in your career, you're going to be reporting to sort of more and more senior management, and the attention deficit disorder just gets worse and worse as you go up the ladder. And so, whoever can communicate what they're trying to get across in as short a time as possible, as clearly as possible, gets their ideas heard. So we're going to be working on that a little bit. Anything else? I think that's pretty much it, guys. I think I've probably already talked more than I intended to. So I'll let you guys go. Any questions?
Professor, for the waitlist permission number.
Yeah. Can you send me
email?
Yeah. Did you already email me to get a permission number?
Yeah, I emailed you before, but at that time I don't think you had the permission numbers.
Okay.
I can email you again.
Yeah, please, Khaled, please go ahead and email me and I'll send you one.
All right. Thank you.
Sure. Anything else, guys? Okay. If not, thanks a lot. Looking forward to working with you guys this semester, and I will see you guys on Thursday.
Thank you, Professor.
Thanks.
Thank you, Professor.
Thank you.
Thank you, Professor.